And we're going to assume that I personally like Venn diagrams to give you sort of a mental picture of what we're talking about. And this area right here is going to be A intersect B. And what we want to do is talk about the base theorem. He says, what is the probability of A given B? This is the starting point. Well, you remember from last time how we did it? We looked at areas and then the probability of those areas existing, or really of the sets, you might say, of the probability of these sets existing. So here, what I told you is if you assume B exists, and you want the probability that this region, that's A intersect B, exists, it's the ratio really of this area to the total area, but really it's the probability associated with those areas. Y'all with me, class? Everybody follow me on this? So, area-wise, it would be A intersect B, and then it would be over P of B. Now, I should say the probability of the intersection of P of B. Does everybody agree with that? This is just straightforward stuff. In his book, he won't use A intersect B all the time. What he'll do is put P of A, B. It's understand, he implies that that is the intersectional area. Y'all follow me? Do you remember this in the book? Now, what he does is going to take this over P of B, right here. And then what he's going to do for this particular case is multiply by P of A and P of A here. Just leave it for a second. Now I come back here. I've done nothing but multiply by a constant on top and the bottom, effectively. Now if I look at P of B given A, well, that's going to be still P of AB here, if you look at that. It's going to have the same intersectional area, but instead of being divided by PB, it's divided by P of A. Y'all with me, class? I'm just trying to make sure you see the logic behind this. And everybody understands the areas associated with this, right? It's A occurs, this is A, and what is the probability that B occurs? That's this intersectional area there. The only thing else. So if I look at this, right here, I get P of A given B is equal to, and if you take a look at this, well, I have P of AB over P of A right there. I just highlighted it. I'm going to circle that stuff. That's this, isn't it? By definition, you'll follow? So I'll put that down there. So that's P of B given A. And then if you take a look at what's left, I have times P of A, and it's divided by P of B. Now I'm not gonna erase anything. I just want to make sure you see the complete logic. There's nothing tricky here, but this gets tricky when it gets complicated. And suppose you had three intersectional areas, P of A intersect B intersect C. Then this thing can get really complicated and confusing if you don't understand the simple steps right here. At this point, I multiply it by P of B on this side, and I'll just erase the one down here. And this is in a nutshell is Bayes' theorem. So it says the probability of A given B times the probability of B is equal to the probability of B given A times the probability of A. It's real important to understand one fundamental thing that probably people make mistakes on. P of A given B is unequal to P of B given A. That's kind of a constant fallacies that people make. And a lot of this stuff, you've got to think about what it's really implying. Y'all with me on this, class? I didn't give you many problems. I gave you problems that I try to expose you to some of the conditional probability things and the mistakes you can make. Now, one other thing I'm going to say, when you have two events that are mutually exclusive or disjoint, and you have the probability of AB, it just is the probability of A times the probability of B. I'm going to say that again. I said it before. For instance, if you have this scenario, and here's A, and here's B, Then if I look at the probability of A, B, that is probability of A times probability of B, because there is no intersecting area. Y'all with me? And that's it in a nutshell. Like these Venn diagrams, at first you're a little just bothered by them because they seem too simple and they don't really reveal anything. As the problems get more complicated, they reveal a lot. And it does get so much more complicated. If you looked at the head, or looked at some of the other problems that I think I put down that Bashir had, I've given you some of the things, it can get much more complicated than what I'm showing you. Now, with that in mind, the next thing I'm going to talk about is, no, I'll leave that up there. Just want to highlight a couple of things that I'm talking about. This is on page 33. And he calls it the law of total probability. And I have some PowerPoints on this, but it basically, if you take a look at the probability of events occurring, and the way I think, I'll show you a PowerPoint on this. So if you have, like, if this is A, and a lot of times he's going to have B1, B2, B3, and you can imagine the whole thing here. This is the set, the entire set. But if you take a look at this, the probability of A occurring can be rendered as the probability of A, and then in union, or I should say, pardon me, he's going to do the intersectional form. I believe in this one. Make sure you get this right. Probability of A given B of I, or B1, pardon me, times the probability of B1 plus the probability of A given B2 times the probability of B2. And what he's doing is saying, now I didn't show any intersection, but there could be overlap. You all follow me on this, guys? But he's saying that the probability of A occurs can be gotten from that. And if you look, this is on page 33, and I hope I'm not doing this in a way that's confusing. It finally says this: the probability of A is equal to the probability of A times the set, S. That's all possible values. Well, if you think about that, because, in fact, what would this be? Well, the way he's going to put this is probability of A, and it's going to be intersect, and then all the possible values, B1, B2, B3, and so forth. B4 keeps going up and up, and he's going to show that the way he wrote it. Oh, I'm sorry, he does a union. Pardon me. My bad. He's going to have this. And then he'll have B1, union B2, union B3, union B3. Because, in fact, remember, if you have these things multiplied by each other, you can put an intersection symbol in there. He doesn't a lot of times. You all with me, class? And then if you have that, well, what is the set? It's just the union of all possible values outside there. And you can include, if you want, I think he does include, this is AI in part in here. Now this is on page, do you all have books, class? You have access to text. This is on page 33. When you see it applied is where it makes sense. Just these laws, law of total probability, and base them until they're applied, it doesn't make sense, a lot of sense. Now, I'm going to try to go through this in a way. The way I usually teach, if I put up any theory, I try to do an example right afterwards. That's the tip. Okay, he has this problem with an urn on page 34. And I want to work through this with you because you're going to see how these laws apply to specific things. And a lot of this stuff seems silly because we're engineers, and these problems don't seem like they're very much applied to electrical and computer engineering. They will be in time. And I have some problems in mind that I'm going to give you. And I have to do with yield rates and stuff like this for solid state processing. But before we get there, I want to keep it as simple as I can. All right, how many looked at this stuff? All right, so this is on page 34. Book. I like to do these. I like problems. It seems to expose things. So we're going to talk about two possible types. It's a simple problem. He has two containers, urns, and they're filled with marbles. So the first one we'll call U1, and we'll call this the red, and is it blue? Blue. Red and blue. This is kind of a classic. And then here's U2. And for U1, is it 5-5?
5-5.
He says he's got 5 red marbles and 5 blue marbles, so 10 total in urn 1. And then in urn 2, he has
2, 4.
All right, a total of 6, 2 red, 4 blue. How many looked at this problem, by the way? By curiosity, did you look at it? No. It's a great problem because it exposes the thought process of doing conditional probability and getting results, real results. So the first thing, he also says that urn 1 has a probability of 2/3, is it?
Yes, sir.
So it's a 2/3 chance of being selected, or 66.66%. And urn 2 has a probability of 1/3. All right, so the event is you're gonna select one of the two. You can't select 0. And from that point, he asks questions. So the first question he asks is one.
It is, after selecting a urn, a marble from that urn is selected. All marbles are equally likely. What is the probability the marble is red?
Okay, that's the first thing. It's going to get more complicated. Y'all follow? He just wants the probability the marble is red. So if you think about this, probability of A, right, is equal to probability of A given B times probability of B plus probability of A given C or whatever times probability of C. Y'all follow me? So this is going to be really the basic law of probability, or I call it the first law of probability, but it's just fundamental common sense, this one. If you look at this, so probability of red, this is just one selection. So first you have to take the probability of urn 1 being selected. Y'all with me on this? Now, if it is selected, the probability of a red occurring if you select that one. And that, I'll just call it probability of red given U1 plus the probability of urn 2. If you haven't looked at this, I want to take a moment, make sure in your mind you're clear about this. Did you look at this? It's a great problem because it exposes the thought process of applying this fundamental law. And then it's going to be times the probability of a red given the second urn selected. Y'all follow me on this? It's a simple problem. And there's no kind of like time varying probabilities or anything like this. What we've got is something that's real simple. It's sort of these are classic problems. Now, all this information is here. This one will be simple. The probability of urn 1 is 2/3, right? And the probability of a red, now he's saying they're equally likely. If they weren't equally likely, we'd have to use weighted probability. So what's the probability of a red if you want to select, just look. 1/2. 5 over 10 or 1/2. Did everybody see that? I want to make sure. 2, 4, 6, 8, 10. We're still missing some people. They must have dropped. Or
They're not coming?
I think it's one person.
Just one?
Yeah.
They're not coming?
Based on the mail list.
Well, there's one more added, and he's right there. There's 2 actually missing. But I'm going to tell you this much. With summer classes, I have people literally come after 3 weeks, and what are we doing? Well, not that you're going to be doing. Anyway, times 1/2. Y'all follow me on this? All right, what's the next part? You might as well do it. Probability of you two,
1/3.
1/3. Times probability of a red with you two. Look,
1/3.
it's gonna be what, 2/6, right? So it's gonna be 1/3. And what is that gonna be? That's 1/3 plus 1/9 is gonna be, is that 4/9? Right? Correct, class? I hope. Is that the right answer?
Yeah, 4/9.
I did a bunch of this stuff last night, but I've been looking at other material to try to make this real, and I've got a PowerPoint. I think it's gonna help. I really, I'm a little, I don't wanna just put it up there before we do these problems. All right, so now, the second part of this, here's where you pay attention.
So now let us change the experiment. Select an urn, select a marble, and remove it from the urn.
You hear that? All right, so we're going to, if we're looking for red, and now this is the probability of a red occurring. Could have been in either urn, right? But now we remove that. So now all of a sudden, if we removed it from here, then instead of the probability of red would be 4/9. Do y'all follow me? And if we did it from here, the probability of a red drops down to 1/5. Y'all follow me on this, class? This is, now it gets complicated. Go ahead, or more complicated. So you remove the red one, go ahead.
I just select a marble and remove it from the urn, and then select another marble and from the same urn.
Okay.
Let R1 be the event that the first marble is red,
That's this.
and R2 be the event the second marble is red.
You got me on this one?
What is the probability the second marble is red given the first marble is red?
All right, now take a minute, think about this. With respect to Bayes' theorem or the fundamental law of probability. Remember, just please follow this. Remember when we had P of, say, P of A given B is equal to P of A, B, or the intersection of A and B over what? P of B, right? Think about this, right? Now, for us, we want the probability of the second marble being a red given the first was a red. Y'all follow me? We've got the probability of the first being a red. Take a moment. You all agree with that? That would be like PB. Do you all follow me? The reasoning. We need the probability of both being red. Follow me? How do we get that?
Use Bayes' theorem.
Well, now we do what? We assume the first one is red.
Yeah.
All right, now what happens? The probability of two reds, so just think about this. We've already assumed the first one is red, right? You're looking and you're...
Yeah, that's just what you do, you just have to assume it.
All right, so...
Why do you do that?
No, well, I mean, he's stating we're going to find the probability of both are red, okay? This is the probability of the first one being red. What's the probability of the second one being red? Now, just follow me. Everybody with me on this? So the probability of the second one being red would be, think about this, the probability of selecting the first of U1, right? Now, if that is selected, and this has got to be out of the same urn, all right? So this is the thing that limits the complexity on this. So if we select this one, then we take the probability of what?
Of getting a red, right?
Of the second one being red
In the urn one.
and the first one being red, right?
Mhm.
All right.
Well, the
So,
marble is removed, right?
but,
The marble has now been removed.
yes,
Okay.
but I mean, just think about this now. So let me try to say this in a way that's a little more clear. So if you think about the possibilities for the first event, probability of red, if you select urn 1, right? That's right here, right? And this is if you select urn 1, right here, then you would remove it, right? Then it would be the probability of the next one being red on top of that. You all follow me in this class? Remember, you need 2 red. So this is going to be probability of urn 1 times probability, and I'll put this of red 1 given U1. And then it's going to be probability of red 2 reds, given R1. Now, if you think about this, this is sort of the chain rule kind of deal going on. If I select urn 1, the probability of a red, given I selected the first one, right? Then if I select the first one, and I got a red, the probability of the next one being red out of that same urn, because he's saying it comes from the same urn, right? Plus, what else? Plus the probability of selecting urn 2 times the probability of red 1 given U2 times the probability of red 2 given red 1, or the first, and I'm just using this as simple. Now in his book, does he have something like that? I don't know.
Yeah.
I don't know the symbolism.
The difference is you have, he puts the probability of, he merges them together. So he has the probability of selecting U1, and then he has probability of red 1, red 2 of U1.
Yeah, well, that's basically, that's this right here.
Yeah.
I like, it's a condition, red 1 first, red 2 second. All right, so now let's just go ahead and do this. So what do we get? Well, this one is just as before, it's 2/3, isn't it? So that's 2/3. Now the probability of a red given the first one selected is 5/10 or 1/2. Just take a moment. You with me? So this is 1/2. Now I have to remove that one. So I'm still on this urn. So I take one away. Now I have 4 red, 5 blue. So it's 4/9 is the next. Do y'all follow me? So this is times 4/9. Plus, then over here it's going to be the probability of the second urn selected, just like times the probability of a red given that, and that's 1/3, isn't it? Yeah, 1/3. And then if we remove that, the next probability would be
R102.
1/5, right? Do y'all see this? Because if you take one away, you're going to have 1 here, 4 here, total of 5, 1/5. Follow me on this? 1/5. Just give yourself a second to think about this. So now we've got the probability, and I'm just saying P of red, red. What do I actually want? I want the probability of red 2, right? I mean, the way I'm saying this, given the first one is red, correct, class? All right, I've got the probability of the first one being red, and that's the probability of the second one being red, so red 2 over red, first, second, is going to be P of, and I'm calling it R1, I'll call it R, I call it RR, so I may as well just RR, over P of R1. And I don't know if he has it the way I'm doing it, but, so this is going to be all this stuff right here. I'm just going to say it right, be divided by P of red. If you divide all that by P of, what was P of red again?
4/9.
4/9. That should be the answer if you check. Is it?
Yeah, that's what he
All
said.
right, now I'm going to tell you one thing about these problems, and this is the thing you got to really look out for. These events, especially the second event and the first event, are not mutually exclusive because it requires you to take out a marble. If they're mutually exclusive, it's different. Do y'all follow me on this? Another thing is about this one. If you think about all possible outcomes, just listen to me for a second, because there's a lot of ways to do these problems, in my opinion, and sometimes you get really confused, especially when you don't have enough sleep. I don't recommend you do these problems with distractions or a lack of sleep. If you take a look at this, what are the possibilities? Well, if I select urn 1, right, I could remove a red one first, or I could remove a blue, right? Those are two possibilities. So if you're going to do the outcome tree, that would be one set of initial possibilities. Urn 1 selected. Just think about this. You could have Urn 1, Urn 2, and you could have red, blue removed. Just think about this and do it binary, right? Well, right there's 8 possibilities if you think about that. You all with me? Now when you do the next one selected after this, you're going to get 8 more possibilities. So now your tree is growing. You're going to have 2 instead of the 4, 2 to the 8th possible outcomes. And it gets really, I hope you all follow me on what I'm saying. The outcome tree gets very large. And what he did is limit the possibilities by saying, if you go to Urn 1, you stay in Urn 1, you pull one red out, then what's the probability of the next one being red? So he's limited the outcome tree. However, what I'm telling you with this I call it, this is Bayes' theorem, but really, or I should say, the fundamental law of, or what did it call? Fundamental law of
Yeah.
Law of total probability. I think it was called a fundamental law of probability. Somewhere back in my mind I have that. But anyway, it's just that the probability of an event occurring, say P of A, is equal to P of A given B times P of B plus P of A given C given times probability of C times all the possible things that can happen. Follow me? And the best way to really get a feel for this is the only way I did it when I was doing it, is do a ton of problems. Because there's so many different things you'll catch your brain doing, and not being able to see how to form these problems into math statements. Okay, that was, is there a second part to this one? We could calculate the probability of a blue given red. We can do every permutation you want, but it's fundamentally the same thing.
Yeah, there's a second part, third part.
What is it?
You don't stay in the same urn this time. You can.
What?
It can be different. You reselect like a new urn.
All right, I'm going to tell you this one. It looks like most of you didn't look at that. Right? Would you do me a favor? I want you to go through that carefully. And you might see it again Friday. I don't usually tip my hat that much, but the reason I'm saying this is that particular problem is great for identifying how to apply this law. So write it down. I know professors don't usually do that. This particular problem, I want you to go through all the possible outcomes. We'll do this too if you want, but the thing about it is think of the changes that can happen. Right now we got 2. What if we had 3? Instead of 2 urns, 3 urns. Or if we had 2, instead of two marbles, red and blue, we got red, blue, and green. You see how the complexity? Now you're going to have that chain rule thing where you're going to have a whole lot more terms possible. That's the thing you got to be guarded against. Make sure you understand the idea. And if you ever really catch yourself in trouble, and see, this changes with time. The probability changed after the first event. And that's what another thing that's different. Always go to those Venn diagrams because they really help in terms of seeing what you need to do. Okay? Any questions before I'm going to move on? I thought that was a pretty good one. Yeah.
How would you do a Venn diagram with this? Like, how would you change the like the circles based on?
Here's U1. Here's U2. All right. Now for U1, you've got red and blue. So, red, blue. Actually, hold it. I'm sorry. I messed that up myself. This should be U1, U2. Red, blue. Red, blue. All right? Now, I'm just showing you, because they aren't, if you select one, you can't select the other.
Yeah.
They have no overlap. Follow me on this one? So if you get the probability that you want selected and you want blue, right? Here you go, write this. I think you'll see this. What's the probability? Just say probability of red. All right. Well, probability of red would be probability of U1, and I think you see that, which is just going to be the area over the set area, proportional speaking. Then it's going to be times what? Times probability of red given U1. And that would be the ratio of red over the total area. Plus probability of U2 times probability of red given U2. Those are the only possibilities because they're disjoint. Now, if there's overlap, then it's different. Then you got to subtract off that overlapped area. But the Venn will help you in this. The thing about this, that's the first Venn, right?
Yeah.
After that, the next one changes because these ratios change.
Yeah, okay.
And then you have to do that. All right. A lot of people, I know when I was taking this stuff, that I had all these questions I was trying to formulate in my head and ask. And I wasn't sure how to ask. There was uncertainty about the possibilities. So a lot of times people try, in my opinion, they try to do this. They're going to try to say, well, the probability of U1 and it being blue, you don't need it here. The only thing they want is red. See, it doesn't ask you what's the probability of the second marble being red, given the first marble was blue. If it did, then we'd have to do a completely different write-up, or a different way of doing this. With me? But these are good problems.
So you're saying we should practice those outcomes, like?
Make sure you understand, yeah, and do this in terms of try to draw a Venn of these things, and then use that Venn diagram to formulate the thing. And by the way, there's a lot of things in here where you'll catch yourself really puzzled. I promise you will. And you'll have to go back, and then it's like, I don't know what happens exactly, but for me, a light dawns. All of a sudden, it makes sense. It gets really crazy when you get conditional probabilities. So what's the probability of the second marble being blue? What's the probability of the first marble being red that the second marble is blue? Now that's an inverse problem. But it's easy to do because if you can get the probability of the second one being blue, given the first one is red, you do the reverse because from Bayes' law, remember? And that works really well. Okay. I'm going to do some problems, but I want to make sure I cover this theoretically. Boy. So I want to tell you this, too. On page 36, there's a binary channel. Did anybody look at that? I get this looks binary channel. I'm used to that, though. Take a look on page 36. I just want to show you this. You all remember we did the thing with the link problem where we had a probability of link working, not working, right?
Yeah.
This is similar to it, but this is actually a real problem. So if we have a sender on this side and call it X, and the values can be 1 and the values can be 0. Please read this one. I'm not going to test you on this Friday, but I want to make sure that you understand it because it's good. And he's saying, and this is the destination. This is a comm link. It could be wireless, it could be wired. Anybody here in communications or do any comm work? If you get out there and do it, you're going to see this is like the beginnings of the classic theory. And then it comes over here. If you have a 1 and you send it and you receive a 1, this is Y. That's one possibility. There's also a possibility if you have a 1 and you're sending it, it comes out. The Y is just the output as a 0, or basically you have an error. Then there's a possibility if you have a 0 here and it comes out as 0. That's another possibility. 0 in, 0 out, and a possibility if you have a 0, it comes out a 1. So he says these are crossover errors, I think he terms it if you look in the book. And y'all have your book here? You have your book. Does he call it crossover error? I'm looking for the
Yeah, it looks like a crossover.
the terminology.
Cross.
Okay, yeah, but he's going to say, I think the cross, if you had a 1 and it becomes a 0, he's saying that error rate is V, and it would be like 0.001 or something. And from 0 to 1, it's epsilon, I believe. And this is the standard, I think it's pretty much the standard way that they label the errors. Usually the rate of V and epsilon are the same. That's what would make it a symmetric channel. Doesn't have to be, though, because ones and zeros, typically if you have things where they're non-return to zero, or they're any type of binary code, usually the likelihood of one error is the same as the other, usually. Now, it doesn't have to be in some cases. So that means the probability of no error would be 1 minus v, and the probability of no error 0 to 0 would be 1 minus epsilon. Now, they want the probability of x equal to 1 given y equal to 1. So we have an outcome and we want to know the probability that it actually is the right outcome. Y'all follow me on that? And then he has something where with a decision tree, based on this stuff, that they'll make a decision because it's going to be statistical and probabilistic. If you get an outcome of 1, the probability that it's right, or the first value is a 1, is going to be based on a greater than of it being a 0. And you're going to see this in a second. Do you see that down there? I forgot what he calls it. It's a Latin term, but
Posterior. P-O-S-T-E-R.
Maximum a posteriori.
Yeah.
Maximum.
in the maximum likelihood.
That rule.
You know what Occam's razor is? Have you ever heard that term?
Yeah.
All right, it's the most likely reason. Like that's the only thing he's talking about. It's a great Latin term. So how do you get this? Think about this. All right. First, can we get the probability of y given x is a 1? Or let's get the probability of y equal 1. Follow me. You see how I'm going to do the reverse on this. I'm going to use base there. All right. So how to get the probability of y equal 1? Well, what will that be? Well, it would be the probability of x equal 1. And here's where this doesn't show it. So I think he says in there the probability of a 1 is p. Take a look at that. Oh, but if you don't, you can see in my book if you don't have it. You'll have access to these texts and stuff.
Yeah, it's the probability that x equals 1 is p.
All right, so he's saying p is the probability of x equals 1. I should say of. And this is x equal to 1. So I want the probability of y equals, actually, what I want is this. I want the probability of x equals 1 given y equal 1. All right, now, what you have to take a look at is, well, we could do it just that way first. Probability of A given B, right, times probability of B is equal to probability of A times probability of B given A. And I'm trying to make it clear. Do you agree with this, class? So now let's define some things. Let's talk about probability, or let's talk about B is y equal 1 and A x equal 1. What I'm trying to do is set this up with base there without confusing you. Do you follow me on this? All right. Now, if we think about this, if we just want the probability let's try this with probability of y equal 1. First, we're going to write that down. And I'm gonna do it this way. So what would the probability of y equal 1 be? First, just following this. So the probability of a 1 is p, right? So it'd be 1 times 1 minus v would be a direct, right? So probability, this would be probability of a 1 occurring would be p times probability of a 1 occurring and 1 occurring here would be 1 minus v. That's probability of a 1 times probability of 1 on the input, 1 on the output, and this is probability of a 1, and this is probability of a 1 on the output given a 1 on the input. So this is the conditional probability there. Does this make sense? I'm trying not to get too confusing in this. There's also what? There's 1 minus p is the probability of a 0 occurring, right? And that times epsilon would be the probability of a 0 occurring and a 1 on the output. Does that make sense? So this times epsilon would be the probability of y equal 1, right? Based on the input. You follow me on that? All right. Now, what's the probability of x equal 1, and that is p, right, by itself. And then the probability all right. So the probability of y equal 1 given x equal 1 is going to be 1 minus v. And let's see, anything else? Let me just see about this. All right, I think that's what we need. So coming over here, and hold on for 1 second. I want to make sure everybody understands what I'm doing, right? I really want this. I'm doing the inverse, you might say. I'm getting the probability of y equal 1 given x equals 1. I'm using Bayes' theorem on this one. So it's, you follow me on this, class? Can you see it back there? All right. So first, you all agree with this right here, right? I mean, what I've shown so far. So if I want the probability of x equal to 1 given y equal to 1, that's like P of A given B. Now it's going to be, in that case, I need the probability of y given x equals 1, which is 1 minus v, right here. And then it's going to be times the probability of x equal 1. And then over here, I would have the probability of y equal 1. So I divide by that, which would be 1 minus p here times epsilon. And in the book, he's going to have we have probability of y equal 1, right? Yeah, you got that probability of y equal 1. Probability for y equal 1. P times 1 minus v epsilon times 1 minus P. Oh. I have that. What I've done is this. I have to take, I'm sorry, I made a mistake. This should be, if I look at this, so this has to be this should be y equal 1, my bad. It's going to be probability of x equal 1. There's probability of y equal 1 given x equal 1. That was my bad. Probability of x equal 1. Now we got it. And that should be, because we divided by that. And that is the probability of x equal 1 given y equal 1. And if you look at that, he has that about the middle of the page on page 37. It's, then he says now we can calculate the posterior, whatever the term is. I even had Latin when I was in high school. And comparing the two, so then we get the probability of x equals 0 given y equal 1, which is the next thing we can calculate. If we have that, and the probability of x equals 1 given y equals 1 is greater than the probability of x equals 0 given y equals 0, then that is the correct decision. You all follow me on this? Now, it seems silly, but what he's doing is this is only for two possibilities for a binary channel, but you can have ternary channels, you can have things with all sorts of possibilities, and there can be a lot of different ways air can sweep in, but this is how a decision would be made, I guess, with this maximum for the map thing, the maximum a posterior area, aerial, or E, I guess. Okay, I'm sorry, I wanted to go through that, but that one is a little odd because what he's talking about is a conditional, really what you need to know is this, don't worry about that maximum thing. The whole idea is, in order to get the probability that x equals 1 given y equals 1, you need the probability that y equals 1 given x equals 1. You need that, and then you have to find the probability of just x equals 1 or y equals 1 in order to do it. That was my only point. I didn't mean to fumble it up like that, but this v and epsilon is not simple. I use a great deal in the way I did it. But did you ever see this in your digital courses, this type of drawing? Like this? No. No. Have you had COM yet?
This is a prerequisite.
Oh, it is? With communications, Dr. Tugnates will teach, and he does a lot of digital stuff, so you'll see variations on what I just showed you, I believe. But they'll be a little different because he'll be more, he's an information theory professor, and he'll have a lot more statistical information about the distributions of the actual likelihood of errors and stuff like this. Okay, got that one. Now, there's an example in drug testing, and there's the diamond network. I'll tell you what, right now I got about 10:35. Okay, so I got roughly 25 minutes here, right? I think. Okay, here's what I'm going to do. I wanted to show you one PowerPoint, then I'm going to go through the problems. But this PowerPoint, some of the stuff may be valuable, and I'll make sure I put it up there. I don't particularly care for PowerPoints, but this one may be valuable. This is something Denny used this. Hope this thing works. I guess it does. Hope the lap. Oh, yeah. Okay. Let's see if we get this. All right, so I want to just say this, that in his book, and I hope get it on slideshow. Okay. This one thing, can you see the cursor up there? All right. The A intersect B is just PAB in our book.
Like the mouse cursor.
Yeah.
It's not on there.
All right, the very first one, you see that A intersect B, the upside down motion? He just puts PAB in our book. In the prior book we had, it always had that intersect. So this is what I was just doing, and if and only if, that's what that IFF means. A and B are independent, PA is P times PB is actually the P intersect B. And then the union, you would always have to subtract off the overlapping area. That was the whole purpose of that Venn diagram. I think most of us see that, right? Okay. Total probability, this is the thing in his book that he calls the law of total probability. And the way he shows it, and I like it better, is just the sum of all probability of B is probability of B given A1 times probability of A1 times, and it goes through the entire set, every possible thing that can happen, and the probability of it times the probability of the event you're looking for, if that sub-event occurs. This is Bayes' theorem that I put down, and this is the usual way it's written. Now, there are very complicated forms of that where they get into, they'll show infinite series and stuff like this. Don't worry about it. Bayes' theorem is simple in essence. It's just saying there's a relationship. If you know any two events, it doesn't matter, say red marble first time, red marble second, anything like this. Well, if you know the probability of red marble first, and you want to know the probability of red marble second, or sorry, probability of the first one being the red marble given and the second is, you can use Bayes' theorem to get it by the inversion. That was one of the things I was trying to show you. Does this make sense to you? I'm trying to be simple about it, but I don't want to be too simple. All right, random variables. Now, I guess I assumed you know this. A random variable is something that's not certain. And usually with random variables, we have statistical ways of describing it. For instance, this only gives you the bounds and the possible values. If you have a resistor and it says it's got a value of 1,000 ohms, but it's got a 5% margin of error, it means it could be between 950 and 1050. That doesn't mean a whole lot to anybody in essence. Like, what's the probability of it being between like 950 and say 975? That would have to do with something called a probability density function that we'll get to. He's just saying this is the simplest way to understand uncertainty. And you probably see these banded resistors, right? That's the first kind of resistor you use. There are discrete and there are continuous random variables. I don't spend a lot of time on this. It's pretty obvious to me. A discrete random variable can have only discrete values, like 1, 5, 7, 9. A continuous random variable can have any possible values between any possible value between 2 points, like between 1 and 7, it could be anything, 6.66665 to 1.3, and there's going to be some statistical way of determining that. There's usually something called a probability density function. How many know what the probability density function is? It is really something that when integrated over all possible values give you a 1. It is all possible values of the probability density function integrated. All possible values likelihood. If you integrate the probability density function over them, you're going to get 1. Go ahead.
Does that have anything to do with the direct del functions or no?
For what?
For like direct delta?
Direct delta functions are simply, they would be used to describe any kind of discrete events.
Okay.
Like if you're rolling dice, you can have 1, 2, 3, all the way to 6, right? So you have the probability density function for that would be, well, there ain't no 0. So it would have a delta of, then it would have, say, a variable n, and would be -1, but it would have a height of 1/6 delta of n minus 1 plus 1/6 delta of n minus 2. So that would be the probability density function for dice. And if you looked at the possible values, just sum them all up, you get 1. I struggle sometimes to explain this stuff. And I don't mean this, to make it clumsy, but a lot of it seems very simple. So random variables. Well, what's a random variable? Uncertainty. Things you don't know the value of. You may know the range or the limitations. So exam grades are a key thing. Exam grades are all over the place, right? And there's no, honestly, I think the distribution in exam scoring is probably as random as anything you can count. And depends on the professor, depends on everything. But that's a random variable. And there's continuous random variables. Now, exam grades can be discrete, they can be continuous. Depends on who the professor is. Now, there's something called a histogram. Are you familiar with a histogram? The only thing it's doing is basically showing you something proportional to what we'll learn to call the probability density function. It shows you the frequency of how many times certain values crop up. In this histogram, can y'all see that? Oops. Sorry, I'm looking at a histogram picture and it's not showing up. All right, so here's what I'm talking about. If you look at this, here's the exam grades. He made them discrete for us. And he shows you the frequency. So the most common exam grades are about 75, it looks like in this one. Now, I'm going to give you a heads up on this. What's coming is if you want to develop, let's assume that you want to get a probability density function that would represent this. Then what you do is say, I'm going to go ahead and assume that I can get maybe a Gaussian curve over that, approximate it. And the area under that Gaussian curve, to integrate it from the lowest score to the top score, has to be 1. Now, if I want the probability that the exam score was between 45 and 60, I would integrate that probability density function, I get it. That's what the probability density function is that you're going to see. You can develop them based on historical information or histograms. With radar, a lot of times with radar, there are ways to simulate target behavior. They're called swirling models, Peter swirling models. And because the target has a known way of motion and stuff like this, you can get the radar cross-section in a very statistically accurate way. It can tell you, have you had EMAG 2 yet? All right, if you have. It's always a struggle to explain stuff. Anyway, what you can do is develop statistically accurate ways of modeling things based on forward solvers. In other words, actual solutions, mathematical solutions to the target. There are also statistical ways. You could take a look and measure an aircraft as it flies over you 1,000 times. They're called Monte Carlo simulations if you're simulating them, just over and over and over again. And then you develop this frequency type behavior. Say that this was radar cross section down here, and that was the frequency that radar cross section occurred when I did these measurements millions of times or simulated. Then I can develop, say, a Gaussian fit to that, and I can develop a probability density function based on statistics. That's 2 ways to get them. Deterministic, yeah.
It's just like a side. Didn't the Monte Carlo simulations occur from gambling? Would you
Probably.
study gambling?
I don't know, but it would only make sense, wouldn't it?
Yeah.
Because
I thought so.
gamblers,
Well, it's also like
gambling is a
Monte
big,
Carlo.
big thing. You don't realize how much money can be made. So these people in Las Vegas and stuff hire the very best actuaries and mathematicians to make darn sure at the tables they can't lose money.
Yeah.
They're going to make sure the overall outcome, the expected value in the long term, is always in favor of the house.
Yeah.
Now, there is something called card counting, and there's a book about that. It's called Bringing Down the House. Has anybody heard of that?
Yeah.
Yeah.
You got to read it. Very clever how a professor decided to recruit some very brilliant students to go out there, and he did.
They made a movie about it.
Yeah.
Yeah.
I don't know how true all the movie is, but that book really, and when, this clever guy, and disguises, all sorts of ways of communicating, everything that the house would kill you for if they get hold of it. I was impressed by it. That'd be a great thing to read before you took this course. It'd get really interesting if I got an idea.
Summer read.
All right, so this is more on histograms, but you get the idea. Now, histograms describe a set of points. I think we got that down, right? I'm about to show you something that is called a distribution function. And so, going back to this histogram, let me explain this. This one I like. Not that one. Nope. Yeah, this one. If you take a look at this histogram, this is the frequency, and I said that if you somehow, you could probably fit a Gaussian curve to that, and you can manipulate the values for the constants in front of that Gaussian curve so that the area under that would be 1. You all hear me? So if you wanted the probability of an event being between lowest value and say 85, it would be the amount of area under that. You all follow me? If you're talking about the probability of something being less than a value of, say, 90, it would be the blue area under there if the total blue area was 1. Make sense to everybody? If the total amount of area under this curve was 1. When you get to 100, the total amount of area is got to be 1, right? Because everything's below that, right? So with distribution functions, what it does is take the integral from up to any given point you define. It says the probability of x being less than or equal to this value. That's the only thing in distribution. You would integrate the probability density function. I know we haven't gotten to it, but this is a good point to at least expose you to the idea. So when you take a look at this, oops. Here's his distribution function that he's trying to give you an idea for the resistor values. If you think about it, remember what I said, that is the integral of what would be the density function from 0, the minimal possible value, up to the point you choose, x. You'll notice it's a linear piece for this resistor at least. It goes up until the probability, this is the cumulative probability. If you pick a value of 1050, the chances that resistor is below 1050, if it's got a 5% tolerance, is 100%. It's 1. That's all this is. It's the integral of the probability density function. And you'll see why I'm doing it, because we're doing conditional probability. This whole chapter is on conditional probability. And don't worry about that one. I'll get to that. I'll get to the stuff more. All right, don't worry. I'm going to put this up here, but it's important to get an idea about why we're doing some of this stuff. Ultimately, we're going to develop statistical tools that are based on the frequency of events occurring. That's the real thing I'm doing. So shut that up. And now get back to these problems. I gave you the problems. How many did the problems at least? Or looked at them? Oh, you got, well, here, take my book. Let's go ahead, because I want to answer these. I'm sorry I took so much time on that. I'm struggling to try to I'm trying to show you why we're doing all this stuff. Ultimately, we want tools to do statistical problems that aren't based on urns and all this stuff. But you have to at least appreciate Bayes' theorem to do those. Okay, what was the first problem? It was
2.1.
Go ahead.
If a fair coin is flipped twice, the flips are independent, and you are told at least one of the flips is a head, what is the probability that both flips are head?
Just twice?
Just twice.
All right, so the both are heads?
Yeah, what is the probability they're both heads?
All right, so he
Given
wants,
one is heads.
he wants probability of heads, given,
At least one is heads.
all right, so that means tails, heads, heads, tails, or heads, right?
Yep.
Now, I'm gonna tell you this one, I assume they're equally likely.
Yeah, in the each.
It's a fair coin?
Fair
Yeah.
coin.
All right, if you look at this, think about areas, all right? If we have heads here, and you take a look at this, if this is A, then B would have heads, but it would have, you get the idea. Follow me on this, class? So it's just what? 1/3, 1/3. I hope that's right.
Yeah.
Follow me, class? There's one other possibility, right? Two tails.
Yeah.
If it were, but that possibility can't occur because he's assuming one head occurs. Do y'all follow me? If you think of the binary, it goes from 0, 0, 0, 1, 1, 0, 1, 1. If one was like in the heads, you could see that this works perfectly, that reason. What's the next one? I'm running.
Two. A fair coin is flipped 3 times. Each flip is independent. What is the what is the probability the first flip is a head given the second flip is heads?
Kenny, did you have a question?
No.
Okay, I mean, it's not, I'm moving
I
kind of,
did these.
what?
I did.
I'm going kind of quick because the first one seemed easy. So say that again for the second one.
So part A is a fair coin is flipped 3 times. Then part A is what is the probability the first flip is a head given the second flip is a heads?
Okay. Now, think before you act. Coin toss. Are they mutually exclusive?
Yes.
If they're mutually exclusive, what do we know? The probability of a second one being a head, or the first one being a head, has nothing to do with the probability of any other heads or tails, right?
Yeah.
Now that's the reasoning, the real reasoning. He does it a little different. So so it's a head in the first or second one?
So a head in so what is the probability the first flip is a head given the second flip is a head?
Okay. All right, second flip is a head, right?
Second flip is a head. What is the probability?
Let me do this. 0, 0, 0, 1, 1, 0, 1, 1. 1 is heads, 0 is tails. Okay. So he wants the probability of the first one being a head, right? So the probability of the first one being a head with probability of 0, 1, 1, 0, 1, 1, according to me, right?
If there's 3 flips, so you have more outcomes.
But I mean, I'm saying this is a probability. I'm not saying that.
Yeah, that's not 3 flips in a row, that's just.
Oh, 3 flips. I'm
Possible.
sorry.
Yeah,
Sorry.
yeah.
I'm sorry. Oh, my bad. This is what happens when we can watch this. So, okay, 3. Basically, we're going to have 8 possibilities. Sorry about this. So, what's the probability of? Say it again.
So what is the probability the first flip is a head given the second flip is a head? Second flip is a head.
Okay. So if you think about this, and I'll do it this way just because it'll help. I think the visual helps sometimes. 0 are tails. There's 8 values there. And he says, what is the probability that
The first flip is a head.
Given
So-
second is heads.
H1 given H2
Yeah.
is heads? Okay.
Yeah.
Given H2 heads. Or flip F. F1 heads, given F2 heads. All right. This really is an area in the simplest sense, right? If you think about this, if you look at given F2 as a heads, all right, and the probability that the first flip is a head. Well, if you look at this, the probability of the first flip being a head would be 4, right? I mean, it would be 4 out of 8, right? Given the probability, so that 4/8, given the probability that the second flip is ahead, right? And you can see the intersecting is right there, right? I hope I did this right. You all follow me on this? Let me just do this better.
Why would it just be there? Why can't it be?
Probability of the first one being ahead, given that, oh, I'm sorry, given that the second one is ahead. Sorry, I was thinking of 2 heads. If you want, we could, just gonna do the inverse in this one. So if we want the probability of the first one being ahead, given that F2 equals ahead. Wanted to do a Venn on this one. Let's see. I think we can. Hold on. Do this again. All right, first I'm going to do second one is ahead are going to be these. This is 1, 2, 3. Second one being ahead. If you take a look at that, right? The probability of the first one being ahead, given that the second one is ahead, which are the ones I circled, is going to be 1 over, I mean, really 2 over 4 if you do it anyways. That's why I'm doing it here, just to show you. Now, you could go ahead and say what with Bayes' theorem, you say probability of the first one, actually, this would be the easiest way to do this because it is going to be area. Probability of the first one being ahead times the probability, or given a second one being ahead, would be equal to the probability of the first one being ahead, given the second one being ahead. Oh, I'm sorry. The probability of the second one being ahead, given the probability of the first one being ahead times the probability of the second one being ahead divided by the probability of the first one being ahead. It comes down to 1/2, no matter what you do. But I'm trying to show this just by identifying the possibilities. Yeah, go ahead.
I don't understand why you can't just go straight to 1/2. Like,
You can.
well, it says, what is the probability the first flip is ahead given, well, who cares about the second? It's going to be 1/2, right? Or is that
As a
wrong?
mutually exclusive. No, you're right. If they're mutually exclusive events, the probability of the second one being 1 or 0 has nothing to do, or a head or a tail has nothing to do with the first one. But you didn't say that in solutions because I looked at that and I was shocked.
Well, because then there's also B and C, and
What does a B and C say?
well, I mean, it doesn't change. Like, they're still independent. They're still mutually exclusive. So
But what does he ask in B and C?
what is the probability the first flip is ahead given there is at least one head in the 3 flips? How does
Well,
that
that's
change?
different though because now you limit the space. Because now look, if you think about this,
The very first.
all right.
very first
See,
set.
now you got
Okay.
0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now he said, read that again.
What is the probability the first flip is ahead given there is at least one head in the 3 flips?
All right, that gets rid of this.
Gotcha.
All right, so they're all there, but the first one being ahead, it would be, that'd be 4/7 over ahead would be divided by 7/7, so it would be 4/7.
Gotcha. Okay, that makes sense.
But it's just reducing, you gotta get rid of that first possibility.
Okay.
Hold it, what was, one? Hang on 1 second. All right, 2, 3, can we just finish this real quick? This one I wanted to just finish. It's not hard. Do it with me. Can you ask, you got your book. What do you got?
A coin with probability P of coming up heads is flipped 3 times.
Okay, go ahead.
So it's a fair coin and the flips are independent. Or wait, no matter. It's not a fair. So what is the probability of getting at least 2 heads given there is at least 1 head?
Okay, now I'm going to show you this one because it's a perfect logical extension of the last one. Possible 3 flips?
3 flips.
0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, right?
Mhm.
So, read the problem one more time.
What is the probability of getting at least 2 heads given there is at least 1 head?
Y'all hear me?
Mhm.
All right, first what we're going to do is find the probability of 1 head. And if you take a look at that, that would be this, at least 1 head. It's all of these, right? That would be the probability of at least 1 head, correct?
Yes.
Well, this is the way I'm going to do it. There's only one where there's no heads. So if I take 1 minus the probability of there is a head, that's the probability there isn't a head, right?
Yeah.
You with me on this, class? So what would that be? Well, the probability that there's not a head would be 1 minus p, right? The probability there's not a head 3 times would be that cubed. Do you agree with that?
Say the
Huh?
probability. Wow.
That's the probability of what?
That there's not a head.
head.
So the probability there's at least one would be 1 minus that. Do you agree with me?
Yeah.
That would be the probability there's at least 1 head.
Yeah.
Now, he wants the probability, so this is the probability there's at least 1 head. Now he wants the probability that
There's at least 2.
at least 2, right? Well, that's the probability of 1. What's the probability of at least 2? These 2, right? That's these right now. Just watch this. So we're gonna on top. Now that's gonna be p, and 1 minus p. So I'm gonna have p squared times 1 minus p here. Now p is the probability of heads. For this one, you got 2 heads, so I have to multiply those p squared here. 1 minus p is the probability of not being a head there. I think that occurs several times. That occurs here too, so it'd be 2, and occurs here too, so that's 3, right? So it's 3 times that plus, not done yet. Now, then I have to take into account 2 heads. There's also this one, right?
Yeah.
So that's just p cubed. So it should be plus p cubed. I think he has this, but I don't remember. Can you see in the answers?
It was something like that.
No, that's it. It's got to be of that form. And this would be the probability of at least 2 heads, given that there was 1 head. You all following on this?
Yeah.
Is that the right answer? Everybody confused?
Yeah.
You got? All right, now that's kind of this is really good to get a visual on this stuff. And we could do this with Venn diagrams, but I'm doing it this way because it's real easy to see why it has to be true, I think. Does this make sense? How many looked at that one? All right, this is a good problem, and it's exposing stuff. I'm out of time. Nobody's pushing me out yet, but I'm going to tell you the other problems. Problem 2.6 is the books problem. I was going to do that one. Did anybody look at that?
Yes.
2.6 is good because it's perfect for a Venn diagram. For history, science, and the overlap area is 20 books, history and science.
Yep.
And then there's one other. And then all the questions are perfect for a Venn diagram usage for that one. Make sure you do it. And then I'm going to give you some homework. I'm going to give you some more stuff to read through. And I'm going to give you a bunch more problems. But please be ready for this one. Okay?
Will the same format be like EMAG where it's at the end of the class?
In the class, it'll be about a 10, 15-minute quiz. And it's closed book, closed notes. And I'll space you guys out and stuff. But
Chapter 1 or chapter 2?
Yeah, I kinda tip my hand, if you know what I mean.
Oh, for sure, yeah.
And you
But
said,
you can still do questions from chapter one, right, or no? Like,
Yeah, I could ask you something real simple. But the whole idea is this, I might ask you to just draw a Venn diagram or something, but I'm not gonna ask you to do that, channel problem. Ultimately, because I don't like the way you formulated the, he really is saying, we're gonna assume it's, if the probability of y is 1 given x, or sorry, x is 1 given y is 1, is greater than the probability of x is 0 given y is 1, then x is assumed 1. That's stupid. That's the way it always is.
And so you said there's like for quizzes and stuff a potential grade replacement down the line.
What?
Because I'm not going to be here Friday because I'm in a
Now,
wedding.
what happens, what I always do is, have you had me before?
I haven't had you with us.
And you can ask these guys, at the end of, towards the end of the course, I give a quiz.
Okay.
If you missed the quiz, it replaces it. If you didn't miss the quiz, your lowest quiz grade is dropped, and that's the replaces.
Perfect.
But, can you get a university approved institution?
I don't think so. I'll look into it more just in case, but
I've always had problems with, not, I don't think anybody's got a monitor in here. If there's a monitored class, I have to get these things, I think.
okay.
I'm just saying, go up there and talk to, what's her name? If you go up to the engineering office,
Okay.
hold on, I'll give you the name of that person in a second.
Yeah, sweet.
She has to give you you have to request a university approved excuse, then I get a message from her, and she'll say, it's not a university approved excuse, but it's up to the discretion of the professor.
Okay.
And the person's name is, I'm trying to think of it now. I'm a little tired today.
Mhm.